Picture this. You're standing outside a burning building. Inside, your crews are battling way more than just flames. We're talking absolute zero visibility, superheated air, and a toxic soup of gases banking down right over their heads. To survive and actually put the fire out, they need to breathe and they need to see. So in today's Explainer, we're zeroing in on a crucial fireground tactic that literally pulls that danger right out of the building. We are mastering negative pressure ventilation, or NPV.
Okay, let's dive into this. Here's our roadmap. First, we'll look at the threat of smoke. Second, the science of negative pressure. Third, the 6-step execution procedure. And finally, we'll wrap up with overarching fireground safety considerations. Let's get into it.
Now, what's really wild here is the sheer urgency of this. This isn't just, theoretical textbook stuff. In the state examiner's Tactical Ventilation Practical Exam, a firefighter candidate has a strict time limit, 4 minutes and 40 seconds. Exactly. That's less than 5 minutes to safely assess the environment, set up the gear, and completely change the airflow of a highly hazardous structure. It just establishes right off the bat how absolutely vital speed and precision are when lives are on the line.
So, part 1, the threat of smoke and why we actually need to ventilate in the first place.
So, what exactly is NPV? Well, negative pressure ventilation is defined as mechanically removing contaminated air from a structure using a smoke ejector or an exhaust fan. The core concept is right there in the name, right? Negative pressure. By cranking up an exhaust fan, firefighters create an area of lower pressure inside the building relative to the outside. And because nature absolutely abhors a vacuum, fresh air just naturally gets drawn into the structure to replace all that contaminated air we're forcing out. The really crucial point here is understanding how this differs from other tactics you might hear about. Take positive pressure ventilation, or PPV. That uses fans at the entrance to aggressively push clean air into a building, which forces the smoke out somewhere else. Negative pressure ventilation is the exact opposite. NPV mechanically pulls the smoke and gases out through an exhaust opening. So instead of pushing air in to pressurize the building, we are literally sucking the bad air out to depressurize it. It's a pull, not a push. Moving on to Section 2, the science of negative pressure. Let's talk wind and airflow. To really master NPV, you've got to understand the science of wind and airflow. This tactic relies heavily on basic physics. Air is always going to naturally move from an area of higher pressure to an area of lower pressure. Always. So when firefighters set up an NPV operation, they are essentially weaponizing the natural wind and the thermal properties of fire gases to do the heavy lifting for them. But to do that, we have to read the environment correctly, specifically the wind. We categorize the sides of the building into 2 types, windward and leeward. The windward side is the side the wind is directly hitting, creating natural high pressure against that face of the building. The leeward side is the exact opposite side, sheltered from the wind, where you naturally have lower pressure. So, if the wind is blowing hard from side A towards side C, side A is windward and side C is leeward. Getting this dynamic right is the absolute foundation of a successful ventilation operation. And this really perfectly illustrates how we use that windward and leeward science strategically. Look at this breakdown. Your inlet opening, where you want fresh air to actually enter, has to be on the windward side at the lowest possible point. Why? Because you want that naturally high pressure outside wind pushing fresh, heavy, cool air inside. Conversely, your exhaust opening has to be on the leeward side at the highest point. This leverages the low pressure on the leeward side to help pull the air out, while using the scientific fact that hot smoke and fire gases naturally rise. It's just smart physics.
All right, Section 3. The 6-step procedure. Let's talk about actually executing the tactic.
Now that we've got the pressure, the wind, and the thermal physics down, we can look at the actual execution. Every single step in the state examiner's practical procedure is completely dictated by the science we just covered, and it has to be performed in a very specific coordinated order. Think of this as your complete mental map for the operation. Step 1. Confirm the order with command. Step 2. Confirm wind direction. Step 3. Provide an opening on the leeward side at the highest point. Step 4. Remove obstructions. Step 5. Place the smoke ejector. And finally, Step 6. Provide an opening on the windward side at the lowest point. Let's break down exactly why each of these steps is required.
So Step 1 is confirming the order with command. Why is this mandatory before literally anything else happens? Simply put, because ventilation operations have to be completely coordinated with fire attack, search operations, the whole shebang.
If a firefighter just independently decides to start pulling air through a building, that uncoordinated ventilation can tragically alter fire behavior. It can draw fire directly toward interior crews, instantly reducing the effectiveness of their suppression ops. You always confirm, Command Ventilation Group, confirming authorization to begin negative pressure ventilation. Moving on to steps 2 and 3. After you confirm wind direction and identify the leeward side, you open the absolute highest point available on that side, something like a second-story window. We touched on this earlier, but it is critical. Heat, smoke, and fire gases are incredibly buoyant. They naturally rise and accumulate at the highest levels of a structure. By positioning the exhaust opening high up, those hot gases can exit much more efficiently. This immediately lifts the smoke layer from the upper levels and dramatically improves visibility for the interior crews operating down below.
Then we hit step 4, which is removing obstructions around your new exhaust outlet. It sounds super simple, right? But maximum airflow is absolutely necessary for effective smoke removal. You might have the best exhaust fan in the world, but if you leave a heavy curtain hanging over the window, you've just blocked your own operation. Firefighters must aggressively and completely clear the opening of drapes, blinds, window screens, furniture, or frankly any debris that might restrict that critical outward airflow. Get it all out of the way.
Now, for step 5, you've cleared the opening and you place the smoke ejector directly within that high exhaust opening to mechanically pull the contaminated air outside. The interior pressure drops, smoke goes out the fan. But wait, think about that setup for a second. The fan is usually a square or a circle, and the window or door is almost definitely larger than the fan, so there is a huge gap of open air all around the ejector. What's the critical missing piece here?
This actually brings up one of the most common points of failure in this tactic. It's a huge, critical note. You must place the salvage cover around the smoke ejector to seal the entire remaining space of the opening. If you don't seal it, sure, the fan blows the smoke out, but the natural draft immediately pulls that exact same smoke right back into the building through the open gaps around the fan. We call this recirculation. Without that seal, your ventilation effectiveness just plummets and your airflow becomes completely uncontrolled. Finally, step 6. Providing the inlet opening on the windward side at the lowest point. Now, why do we do this last? Well, as the smoke ejector removes air from the structure, replacement air obviously has to enter. By waiting to open a ground floor window or front door on the windward side until the fan is actually running, we ensure that fresh air intake forms a controlled, deliberate flow path. We are forcing the clean air to travel from low to high, pushing the contaminants exactly where we want them, straight toward our sealed exhaust fan.
All right, section 4, fireground safety considerations. How we stay alive doing this.
We really have to remember that this entire operation takes place in an IDLH environment, immediately dangerous to life and health. Before beginning any operations, the candidate must confirm these non-negotiable safety rules to the examiner. You must wear full personal protective equipment and go on air using your SCBA in those IDLH conditions. You must instantly identify a secondary means of egress just in case an emergency evacuation becomes necessary. You've got to coordinate to ensure gas and electric utilities are shut down, and you must constantly monitor structural stability and continuously evaluate if your ventilation is actually working or if conditions are just getting worse. Which leads us to a final, pretty critical question to leave you with today. Let's say you've perfectly executed the 6 steps. The fan is sealed, the flow path is beautifully established, but a fireground is a dynamic, living beast. What happens if the weather suddenly changes and the wind shifts 180 degrees? In a rapidly deteriorating fireground, is your controlled airflow path still saving interior crews, or are those shifting winds now fighting your fan and putting everyone in deeper peril? It's a stark reminder that in tactical ventilation, situational awareness can never, ever be turned off. Thanks for hanging out with me for this explainer. Keep analyzing, keep learning, and as always, stay safe out there.